All right, everyone. Today we're tackling something that's, frankly, one of the most critical integrity threats facing the systems we're all building: training data poisoning. And look, this isn't just some theoretical academic problem. It's a very real, foundational vulnerability that can turn our most powerful, most expensive models into serious liabilities.
So let's just dive right in. We're not going to start with a simple definition, though. We're going to start with a really counterintuitive problem, one that completely challenges a core assumption I think many of us in this field hold about building AI.
You know, the conventional wisdom in machine learning has always been pretty simple, right? Scale equals robustness. Bigger models, more data, that means better performance, more resilience. But it turns out, when it comes to the threat of data poisoning, that assumption is not just wrong, it's dangerously flawed.
And this is exactly where our intuition can lead us astray. New research shows that as our models get bigger and bigger, that massive capacity actually allows them to memorize malicious patterns from just a tiny, tiny fraction of tainted data. And the crazy part is, it does this without hurting their overall benchmark performance. So what does that mean? It means our race toward ever larger foundation models might actually be making them more vulnerable, not less. Okay, so if we're going to defend against this, we first have to really understand the adversaries playbook. So let's break down the anatomy of a typical data poisoning attack. Now, the key thing to get here is that this isn't an attack on a deployed endpoint or an API. It's an attack on the foundational learning process itself. By corrupting the training data, an adversary literally bakes a flaw directly into the model's weights, a flaw that's just going to sit there for its entire operational life. So, adversaries really have two main goals. On one hand, you've got your targeted attacks. Think of these as aiming for surgical control over very specific inputs. They're incredibly stealthy because they don't mess with the model's overall accuracy. On the other hand, you have the broader non-targeted attacks. These are designed to just degrade performance across the board and make the model generally unreliable. They're a lot noisier and, frankly, easier to catch with standard monitoring. And that brings us to the most dangerous type of targeted attack, the backdoor. You should really think of this as planting a hidden vulnerability, a kind of sleeper agent that just lies dormant deep inside the model's logic, waiting. This lifecycle shows you exactly how it works. First, the attacker injects data with some kind of hidden trigger. The model, just doing its job, learns a false correlation. Now, the crucial part is step 3. The backdoor remains completely dormant. So the model passes all of your validation tests, all your benchmarks, but then later, out in production, the attacker presents that trigger and bam, the model executes the hidden malicious command. And just when you think it can't get any harder to detect, you've got to consider clean label attacks. Okay, this is wild. Here, the poison data is actually labeled correctly. A picture of a dog is labeled dog. The malicious payload is hidden in these tiny, subtle feature perturbations, totally imperceptible to a human reviewer, but they're designed to create a feature space collision that forces a misclassification later on. This stuff bypasses even manual data inspection. It's the ultimate stealth. So where are we most vulnerable? Let's take a hard look at the attack surface for the very systems that are defining our industry right now. And this really highlights the massive asymmetry of the problem, you know? As defenders, we have to secure petabytes and petabytes of data. An adversary? They only need to successfully poison a minuscule fraction of that to win.
How small of a fraction are we talking about here? Well, according to NIST, as little as 0.001% of poisoned data can be enough to cause a catastrophic model failure. For a web-scale dataset, trying to find that tiny needle in that enormous haystack, well, it's a monumental challenge. This puts our most important, most widely used systems directly at risk. LLMs, because they ingest these vast, untrusted datasets from the web. Federated learning systems, well, they open up countless potential injection points from all the clients. And RAG systems, they introduce a potent and very new attack vector, poisoning the external knowledge base. Let's actually look at a concrete example that demonstrates this RAG vulnerability perfectly. This is not theory. This is a practical proof of concept that just came out in 2024. So, this research showed how injecting just a handful, literally 5 malicious files into a knowledge base, like, say, your company's internal documentation, could completely compromise a system like Microsoft 365 Copilot. But here's the most alarming finding, the part that really got my attention: the persistence.
The model actually internalized the false information, and it kept generating it even after the source documents were found and deleted. This makes cleaning up after an attack incredibly difficult. Okay, so that's the scary part. How do we fight back? Well, there is no single silver bullet here. Let's be clear about that. The only viable approach is building a resilient, multi-layered defense that spans the entire MLOps lifecycle. What this really means is that we have to stop treating security as some final checkpoint before deployment. It's not going to work. It needs to be automated and integrated from the very, very beginning. We need to secure the data, we need to fortify the model itself, and we have to implement really robust operational controls around the entire pipeline. And this strategy really requires defense at every single layer. At the data layer, that means automated validation and, crucially, data provenance so you can track the lineage of everything. At the model layer, we can build in more robustness through techniques like adversarial training. And then, throughout your operations, we have to enforce strict security fundamentals, principle of least privilege, sandboxing any new data, and continuous monitoring against a trusted, clean baseline. And look, when you do detect an issue, and you have to assume you might, your incident response has to be swift and decisive. You use those provenance logs to isolate the poison. You roll back to a versioned, known good state for both your data and your model checkpoints. And finally, you have to perform a full retraining from a verified clean baseline to completely purge that malicious influence. So let's wrap up by looking at the strategic imperative this creates for all of us, as the engineers actually building these systems. This forces a fundamental shift in our mindset as a field. For too long, we've chased benchmark performance, accuracy, F1 score, as the primary, sometimes only goal. It's time to elevate security robustness to a first-class metric and treat it as just as critical as anything you'd see on a leaderboard. And this threat is not standing still. It's evolving. We have to anticipate the commoditization of these attacks, things like poisoning as a service offerings on the dark web. Adversaries are already using AI to generate more sophisticated attacks, and our reliance on public model and data repos means the supply chain is going to continue to be a primary battleground. Ultimately, this requires a total shift in our security posture. We have to adopt a zero-trust mindset for our data pipelines, treating every single data point as potentially hostile until it's been verified. You have to assume you're vulnerable, and you have to automate your defenses accordingly. So this leaves us with a final and, I think, pretty critical question. As we integrate these models into finance, into healthcare, into critical infrastructure, the stakes get higher every single day. The question we have to ask ourselves as engineers is this: are our defenses evolving as fast as our models' capabilities? Because in this new landscape, vigilance isn't just a best practice, it's the price of integrity.